how do I say this? We're continuing. This is a part. Once again, this is part 3 of section 4.5, and we at the end of part 2 we established that the number of vectors in a basis, that if I have a basis with n vectors, then every basis is going to have n vectors. Now this is going to allow us to define finally the concept of dimension. And here we go. If a vector space V has a basis containing n vectors, now we just learned before that if it has one basis with n vectors, then any basis, all the bases, I don't know, plural, all the bases are going to have n vectors. So that number n is now called the dimension of the vector space V. And that's because, every basis has n vectors and dimensions. And we're going to see that this really fits in with some of the, so on and so forth. So, by the way, if the vector space is just a zero vector, then we say the dimension is 0. So if the entire vector space is just one point, then as a 0, which is true. A point, in geometry, a point is 0-dimensional, a line is 1-dimensional, a plane is 2-dimensional, so on and so forth. And that's exactly what we have over here, meaning the dimension of Rn is n. According to, I mean, in our familiar practice, and in according to this new definition, the dimension of Pn, that's the polynomials of degree n or less, with the standard operations is going to be n plus 1. Again, this is something we've seen. And if you look at all the matrices, Mn, the dimension is going to be m times n. Because remember, if you have a 3x2 matrix, so you have 6 different entries, and each one is like its own little dimension, so to speak. Okay. Now let's so if W is a subspace, if W is a, here we're making an interesting, I think an interesting comment. I think it might be obvious, I don't know, but that the subspace, the dimension of the subspace is going to be less than the dimension of the original space. If we're talking about finite dimensional, when you're talking about infinite dimensional, then all kinds of weird. When you deal with infinity, a lot of crazy things happen. But with the finite dimensional thing, the dimension of a subspace will be less than or equal to the original. Anyway, let's look at some examples here. So here we have some interesting subspaces of R3. So the first guy here is the set of all vectors in R3, which are of the form D, C minus D, and C. So basically, if like so in other words, that's my X and that's my Z, and the Y is equal to Z minus X. Pretty much is what it's saying here. And that's one subspace. A second subspace we have is 2B, B, and 0, meaning that all the vectors are in all the vectors are in this form, 2B, comma B, comma 0. So the Z values are all 0, the Y values or whatever they are, and the X values are double whatever the Y value was. Anyway, let's see what so these are subspaces. Let's see what dimensions they are. Now we know that they have to be dimension 3 or less. Let's figure it out. So when you write, if you have D, C minus D, and C, I can break this up. So I want to separate out the C's and the D's to make it easier. So so D, C minus D, C, that is equal to OCC plus D negative D O. Because if I add these up, the D plus 0 is my D, the C and the minus D is C minus D, and the C here with the 0 there gives me that C right there. So I'm taking this vector, breaking it up into 2 vectors. Now I'm sort of factoring out the C and the D. So what's happening here is that these two guys, the 0, 1, 1, and the 1, negative 1, 0, that really becomes my spanning set. These are linearly independent vectors, and they span the entire, they span the entire subspace. I'm not saying they span the entire R3, I'm saying they span the entire W. And we can show, and it's easy to show that these are linearly independent. We learned how to do. That's why you see this is the way linear algebra kind of builds and builds and builds. We showed in the last section how to show that a set is linearly independent, and now we're using these skills to look at dimensions of a vector space. So linear algebra is, like I say, it's a whole different system. And by now you're probably noticing that this is very different than what you always thought of it, what you always called algebra, because typically in an algebra class that you've always been to before this, it's always been, a factor this polynomial and solve this equation and expand, FOIL, whatever, multiply this stuff, whatever. Linear algebra, as you can see, is quite different in the sense that we're creating, I shouldn't say different, but we're creating a whole kind of system. Now, linear algebra is a lot of, it's a lot of creation, and it's for good purpose because it's extraordinarily powerful and extraordinarily useful as we see more and more. Continuing on, we see for B, well, B, I could easily just factor out the B, this B. So this vector becomes B times 210, which means that W, the subspace W, is spanned by the vector 210, which means it's one-dimensional. So the first one, so this guy was two-dimensional, A was two-dimensional, and B is one-dimensional, and that's the way it works. Next, so I want to find the dimension, and again, once I have one basis with then every basis will have the same number of vectors. Let's find the dimension of the subspace of W. So we have a subspace W, which is a subspace of R4, and it's spanned by these three vectors, V1, V2, V3. Here's my V1, here's my V2, here's my V3. Now, again, we could solve this. We learned how to solve this again in previous sections. But we're doing the work for you. We're going to say that V3, vector 3 is equal to 2 times vector 1 minus vector 2. So if you double this and then you subtract that, you wind up getting this. And let's just look at the first component. Doubling -1 gives me -2. -2 subtracting 3, -2 minus 3 is -5. So the first one works out. They all work. They actually, when you go through, they all work out. Now, so again, this is an example of finding a dimension. See, if I would say find the dimension of R4, well, we know it's 4, but this is a little more challenging because, so I'm sorry. Since we see that V3, I really didn't complete the thought. Since we see that V3 is equal to 2V1 minus V2, it means that this set is not independent, and V3 can be expressed as a linear combo of 1 and 2. So therefore, if I just chuck V3 out of the set, so to speak, and I just consider a new set, V1 and V2, well, V1 and V2 are linearly independent because they're not. Remember, whenever you have two vectors, as long as one is not a scalar multiple of the other, they're linearly independent. So this gives me, because they are linearly independent, this gives me a set which is now going to span everything. So S1 of just V1, V2, that's going to span everything that the original set spanned, because this 3 doesn't add anything to the span. So hence, this is going to be a basis. It's linearly independent. It spans all of S. Hence, this is going to be a basis of W. Spans all of W, and it's going to be a basis of W. Two vectors. So this is two-dimensional. This is two-dimensional. So this is a two-dimensional subspace of R4. And let's continue. So you see, notice that some of you might have said, "Hey, our subspace is defined by these three vectors." Three vectors, 3 dimensions. But that's not good enough. You got to make sure that those three or whatever vectors are indeed linearly independent or not. Okay, let's go on to another example. Finding the dimension of this subspace. Well, M22. So this is really 4-dimensional. And we want to look at a subspace of all symmetric matrices. Symmetric matrices are the ones that are, well, we know what they are. So a symmetric matrix looks like this. The A and the C can be anything but these two guys have to be equal to each other. This is what a 2x2 symmetric matrix means. Well, I could take this and break it up into sum of three different matrices: A times 1, 0, 0, 0, B times this guy, and C times that guy. For example, because and these and if I add these guys up, I'm going to get A, B, B, C. So this set 1, 0, 0, 0, 0, 1, 1, 0, 0, 0, 0, 1. This spans the entire W, the subspace of symmetric matrices, and it's really easy. I mean, you can practically see it, but you could show it the way you can show it by the techniques that we learned. Or you could just kind of see it that this is linearly independent. Why do I say you could just kind of see it? Because I can add these two guys all day and all night, but I'm never going to get this. I'm never going to get that one over there. How am I going to produce that one? Because if I add vector 3 and vector, I'm going to call this vector v1, v2, v3. If I add v2 and v3, I can add any combination I want of them, but I'm never gonna not get a 0 in that first position. So how am I ever going to produce that one? So obviously, I need this. I cannot express this vector as a scalar multiple as a linear combo of these guys. And similarly, I can't take a linear combination of the first two vectors because I'll never produce that. I'll never produce that one down there because I have a 0 and a 0, and I can never express the middle vector because I can add the first vector and the third vector all I want. I will never, but I'm going to just have zeros, like up on the upper right. I'll never produce those two ones. So you can kind of just see it. I mean, we learned the sophisticated ways of doing this, but in this case, you can just kind of see it. So now we can. I just want to give you. I'm not going to prove this right now. This is a theorem test for a basis, and this is really makes our life easier, which is what we're really trying to do. You may think that my job is to make your life harder. A little bit it is, but really we're trying to make your life easier by giving you some very, very, very powerful concepts. And basically what this theorem is saying is that, and this is really important to remember, it's going to make our lives, it's going to change our lives. If you have an n-dimensional vector space, so we're given that the vector space is n-dimensional. So if we have a set of n vectors, the same n, this n and that n is the same n. If we have a set of n vectors, once we know that those n vectors are linearly independent, then we know that they're going to span the vector space. Similar on the flip side, that's what number one is saying. What number two is saying is that if we have n vectors and it spans the vector space, then it has to be linearly independent. Meaning to say that if I have n vectors that are linearly independent, this has to be a basis. If I have n vectors that span, then it has to be a basis. So, which makes our life easier because normally, if you want to prove that something is a basis, you have to show that it spans and that it's linearly independent. You have to show two things, but this theorem is telling us we only have to show one thing, assuming that the set we're looking at is n vectors, the same as the dimension n. So if you're lucky enough to have that such a set, then you only have to show one thing and you're good to go. Now here's let's look at this set of vectors here. This is a very scary look. This is what we call M51. So they're 5x1 matrices, which is basically just a column matrix, 5-row column matrix. And we want to show that this is a basis, that this set here is a basis. So what we're going to do is use it, Theorem 412, which is what we just learned, is going to show that we only have to show one thing. We don't have to show two things. We can either show that this is linearly independent, or we can show that it spans. Well, let's go for linearly independent. So to show that S is linearly independent, we're going to form a vector equation. We're going to look at C1v1 plus C2v2 plus C3v3, C4v4, or C5v5, set that equal to the zero vector. And if we could find non-zero solutions, then it's dependent. If we can only find zero solutions, then it's independent. Well, if you look at these equations, they actually are very easy to solve. because you have a whole stack of equations here. Well, from the top equation, I see that C1 is equal to 0. Once I know that C1 equals 0, then I get 0 plus C2 equals 0. So that means C2 equals 0. Once that's 0 and that's 0, then I'm left with 2C3 equals 0. So C3 is also equal to 0. Once these three guys are 0, then that fourth guy is 0. And it kind of goes down the line like a domino effect, sort of a cascading domino kind of effect. So you see from here that the only solution of these of this system of equations is the trivial solution, meaning where everything equals 0, which means all the variables equal 0. That tells me that S is linearly independent, and that's it. I don't have to show any more. I'm done. And that's what the beauty of theorem 412. Instead of saying, okay, we're halfway there, now we got to show that it spans. No, we don't got to do that no more. We have this fabulous theorem. Yay! Sometimes, like I say, theorems are there to make. Theorems are your friends. Theorems are your friends, and they're trying to make you better and smarter and faster and awesome, more awesome. So I guess what I want to say, and I was trying to say this before, is that you see that linear algebra is very different, quite different than elementary algebra, intermediate algebra, college algebra, all the stuff that we did before now. We're creating a whole, we're using matrices and vectors and all this stuff to create a whole kind of new system, very different than what we've done before, yet very similar to what we've done before, very based on what we've done before. And it's just going to make things easier, better, faster, more powerful. It's linear algebra is the most amazing. I have to say, it's just the most amazing topic that there is. So I'm going to stop the recording now, and we're going to next time we meet, it will be at section 4.6. And here we go. We are